Hi students, welcome to Math4U. In this session, I'm going to explain to you how can you understand the decimal expansion of a rational number is terminating or non-terminating, repeating. So we have some theorems based on this to prove. Okay, so let us see the first theorem based on this. Theorem 1.5, you can see in your textbook as well. Let x be a rational number whose decimal expansion terminates. Okay, then x can be expressed in the form of p by q, where p and q are coprime and the prime factorization of q is of the form 2 raised to m 5 raised to m, where n and m are non-negative integers. I think it's a bit confused now. So I will explain to you with an example so that it will be very clear for you what does it mean. Okay. So as an example, I'm going to take 0.375. So what does the first sentence say? Let x be a rational number whose decimal expansion terminates. So this is that x, the rational number whose decimal expansion is terminating, right? X can be expressed in the form of p by q. So now I'm going to second step. Now I'm going to express this of the form p by q. How can we express this? 375 divided by 1000, right? Yes. So I have expressed it of the form p by q, where p and q are coprime and the prime factorization of q is of the form 2 raised to n 5 raised to m. How can we do that? The denominator, we have to do the prime factorization. So 375 by 1000. Can we write it as 10 cube? Yes. Now I'm going to write again it of the form 2 cube multiplied with 5 cube. Okay, so you got as a 2 cube multiplied with 5 cube, and I'm going to change the numerator as well, do the factorization for the numerator as well. So that can be expressed as 3 into 5 cube. Okay, I'm not doing the prime factorization here. As we are reaching the end of this chapter, I know you are very thorough with that method. So this we can do the cancellation for this 2. This is of the form now what 3 by 2 cube. So before this 3 by 2 cube, you can see here what is the denominator format. What is the denominator format? What is the denominator format? 2 raised to n 5 raised to m, right? And the prime factorization of q is the form 2 raised to n 5 raised to m, where m and n are non-negative integers. So you got here q as 2 raised to 3 and 5 raised to 3. This is of the form 2 raised to n and 5 raised to m. Is that clear? What does the first theorem says? I will give one more example based on this. Example 2. Let's see one more example. So I'm going to write another decimal 0.0875. First, what we have to do, we have to convert it into p by q form. So how can we write that? 875 divided by how much it will come? 10,000. That is 10 raised to 4, right? Yeah. So that is equal to, you can write it as, how can we write now? This you can cancel. You will get the denominator as 2 raised to 4 into 5. Okay. So now you can see the denominator. It is of the form 2 raised to n 5 raised to n. Right. What does this mean? This means that if x is a rational number whose decimal expansion terminates, it's terminating here, right? And it can be expressed in the form of p by q. Okay, and p and q are coprime. Okay, and the prime factorization of the denominator q is of the form 2 raised to n 5 raised to m, where n and m are non-negative integers. So this is the theorem 1.5 explains. I hope it is clear. So let's move on to the next theorem. Theorem 1.6. What does theorem 1.6 says? Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n 5 raised to m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. So we are proving here we got x as a p by q form, and we are converting the denominator q to the form of 2 raised to m 5 raised to m. Then we can say that x has a decimal expansion which terminates. So we concluded here, if we get like this form the q, then it has a decimal expansion which terminates. So let's see an example for this. Okay, I'm going to take here one number, that is, let it be, okay, so let it be 13 by 125, and I'm going to do the prime factorization of the denominator. Okay, so how can we do the prime factorization? 13 into, I'm going to first I'm converting the denominator into 5 raised to 3. Is it 5 raised to 3 now? Yes. So now what I'm going to do is I'm going to multiply the numerator and denominator with 2 cube. So 13 into 2 cube by 5 cube. When I'm multiplying the numerator, we have to multiply the denominator. Or when we multiply the denominator with a number, you have to do the same with the numerator also. Then only it will be correct, right? So this can be changed to 104 by 10 cube. Right? So before going into that, what we need, that is what we have to check. If we are getting the denominator in the form of 2 raised to m 5 raised to 3, 2 raised to n 5 raised to m, or 2 cube and 5 cube, what can we conclude here? This decimal expansion is a terminating one. That means when you are doing this, okay, you will get the answer in the form of 0.104. That is a terminating. Is it clear? I will show another one more example. So another example is 3 by 8. So 8 you can represent in the form of 2 cube, right? Now we need a 5 also, right? So I'm going to multiply the denominator with 5 cube, and the numerator is also with 5 cube. So what you will get? 375 by, yes, that when you calculate this, you can understand what you will get. So I'm not going to explain it here. Okay, we can explain it in the next theorem. So what, according to this theorem, what we need, we have to get the denominator in the form of 2 raised to n, 5 raised to m. Then we can say that it terminates. Let's see whether it terminates or not. Okay, so 3 into 5 cube by 2 cube into 5 cube. The answer will be 0.375. So it is terminating. So the rational number, which is of the form p by q, and the denominator, we can convert it into the form of 2 raised to n, 5 raised to m. Then we can say that the decimal expansion of that rational number is a terminating one. Is it clear? That is theorem number 1.6 says. So the next theorem is, let's see, theorem 1.7. Let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to n 5 raised to m, okay, where n and m are non-negative integers, then x has a decimal expansion which is non-terminating repeating. So how can we say this? How can we conclude this? Okay, so I'm going to do an example over here. So p by q form, 1 by 7 is of the form p by q, right? I'm going to do the division of this. Let's see whether it is going non-terminate. Okay, so 1 by 7, you know how to divide this. I'm going to do the division point. We can write 7 one time, so 3, then again 30, 4 times 28, then again 2, 0. You can see here 2 times, then 14, then 6, 0. How many times? Yes, 8 times 56. So again you will get 4. So what do you see here? It is not ending, right? It is a repeating or non-terminating, right? It is going on when we divide this. So what we can understand, if P by Q be a rational number such that the prime factor of the denominator, that is Q, is not of the form 2 raised to n 5 raised to m, then we can say that it is a non-terminating repeating. So I will give another one example to show this. This is P by Q, which is not terminating, right? So let me show you an example for non-terminating repeating. So I'm taking one number in P by Q form, 77 by 210. Okay, this we can split as 11 into 7 factorizing, and the denominator as you can see here 30 into 7. Okay, so when you do the calculation, you will get 11 by 30. Now the Q is here 30, right? So we should get Q as of the form what 2 raised to m 5 raised to n to say whether it is terminating. If it is not of the form 2 raised to m 5 raised to n, we can say that it is non-terminating repeating, right? So I'm going to check whether 30 is what all are the factors. So you will get 2 into 3 into 5. So you can see here the denominator is not of the form Q is not, denominator means here P by Q, so Q, right? Q is not of the form 2 raised to m into 5 raised to n. Therefore, and also it has a factor 3 in it, right? You can see that. Therefore, the decimal expansion of 77 by 210 is non-terminating repeating, right? So this is non-terminating repeating. And I will show you one more example for this to show how can we recognize this. So the third example, I'm going to give you a number that is 129. Okay, 129 divided by, this is directly given, this is from your textbook, 2 square, 5 raised to 7, 7 raised to 5. So by looking into the number itself, P by Q, the Q itself, you can say that here this is not of the form of 5 raised to n, 2 raised to m, because it includes 7 as a factor also, right? So this is non-terminating repeating, right? So how can you understand this? You can understand by looking to the Q, right? So what we have learned today, so we can say that if a decimal expansion terminates, then the denominator will be of the form 2 raised to n, 5 raised to n. That is the first theorem in this we have learned. Second theorem means if P by Q is a rational number and the prime factorization of the Q is of the form 2 raised to n, 5 raised to n, then we can say that it is a terminating decimal expansion, right? And the third one, what we have learned just now is if the denominator Q is not of the form 2 raised to m 5 raised to n, we can say that it is a non-terminating repeating one. So is the session clear to you? Bye. Thank you.